Hi, in today's video on combinatorics, we'll be going through distribution problems. So this is a very important problem when dealing with counting, and there's many studies about it. And that is how we want to distribute objects into boxes. And this can be classified into 4 types. So let's say we have R objects and N boxes. And then the objects are either distinct, the box is distinct, identical to distinct, you want to distribute distinct to identicals, and identical to identical. The last 2 types, where you're going to identical boxes, it gets a little bit more tricky and to be talked about in separate videos. But let's go through the first 2 types because they are fairly simple. So let's start with the first type, where there's R distinct objects into N distinct boxes. What does that mean? It means you have a linear order actually. So you have like 1 to N boxes and they are distinct. So they can be labeled 1 to N. Then now you want to put the objects which are also distinct. So the ordering matters, you can think about it. Now, there are a few conditions and they lead to different type of values. The first one is if each box holds at most 1 object. Why I say at most is because there could be less than N objects. If there's more than, by the pigeonhole principle, some of the boxes will hold 2 objects. But let's say R is less than N. Then, basically, it is NPR. And the reason for that is, of course, the same. Now, you have more boxes than objects. So, you can replace this N here by R. The first object has N choices. The second object is N minus 1. And the R object is N minus R plus 1. So, when you multiply them all up, it's just NPR. So that's basically it. And then now we move on to the second scenario where you're again doing distinct to distinct, but now each box can hold any amount. So like how we did the formula last time, for N to power R, it is because your first object has N choices, your second object also has N, and your R object has N. So it's N to power R. Hope that easily shows why these 2 scenarios have these values. Now we move on to the third scenario of a distinct to distinct case. And that's if each box holds any number. So let's imagine you have the boxes already here. Now I place my first object, which has N choices, here. Because you're placed in this box, you can think about it as the box being in this format. Then you put your N over here, so I can slot in a line here. This is a thickened line denoting my N. But can you see that because the ordering within the box matters, now you have 2 slots within a box. And so this 1 box now become 2. And so there's actually N plus 1 choices for your next object to choose. So it's N times N plus 1 all the way N plus R minus 1. If you rearrange that terms, it is N minus 1 plus R to all the way to N. And so that is actually given by this formula. R plus N minus 1 factorial over N minus 1 factorial. Hence, you can see these are the 3 scenarios for which a distinct to distinct distribution can occur. And if any other scenarios, you can play around with it and understand that if you are distinct to distinct, regarding which one has more or less, then you choose to put whoever first. Like if there is less objects than boxes, then your objects can choose the box. And if there's more boxes, then less boxes than objects, then you can think of it, there will be some boxes with more than one object, so you can instead take the boxes and you can slot the objects into the box. So that's basically it for the type 1 problem of distribution. We'll move on to type 2 now, which is identical to distinct. For identical to distinct, you can think of it in terms of a binary sequence or a integer problem solution. Why? Imagine that you have an integer solution, which is your distinct boxes. Your identical objects will be the number here, let's say R. So to make this more precise and general, we'll do all the way to x to n R. Then these are representing your identical, because x to n, there's n minus 1 lines by the stars, and or you can call them bars. By the stars and bars, to put these R boxes is like putting 0, 0, or like then a 0 at the end. And then this represents like there's 2 here, and there's 2 objects here, and here is 1 object. So that's why they're identical, because they are the same zeros. And so that's the reasoning behind why we can think of it as a binary sequence. Now, if you know that each box has at most 1 object, then it just means that you choose R of these boxes to have an object, if you get what I mean. So like, imagine you have n boxes, and so you got n boxes, and you only know R of them needs to be placed in a box. So you just need to choose, like let's say you have 5 boxes and you want to distribute 2 objects, and each box can only hold at most 1 object. Then it is just choosing 2 of the 5 boxes to put the 1 object, the identical object, and you don't need to arrange them in any order. That's why the first scenario is n choose R. The second scenario is the H formula. Like I've explained, using the binary sequence, if you can hold any amount, you just n plus R minus 1 choose R. And again, why is that so? If you watched our previous video on counting, it is just counting the number of binary sequence, because it is the stars and bars technique. And then if no box is empty, well, then obviously by the integer solution problem, what you do is you take away n of this from the R first, and you place them in. So everyone gets 1 object. Then there's R minus n objects left. And so you want to distribute these R minus n objects into n boxes, and that is just plus n minus 1 choose R minus n, which results in R minus 1 choose R minus n over here. Hence, in these 3 scenarios, you can see it's fairly simple to distribute identical or distinct objects into a distinct box, which is either you choose or you permutate in distinct to distinct. So this is the video to encapsulate the first 2 types of distribution problem. In the subsequent videos, I'll be doing the other 2 types, and I'll be exposing you to other ways to solve distribution problems, such as using generating functions. But because that's a little bit more complicated, it won't be in this tiny video, and hence I hope you have enjoyed this bite-sized introduction into the distribution problems and how to solve them when you want to place objects into distinct boxes. Thank you for listening, and please feel free to like, share, and subscribe. And you have any questions, you can leave them in the comments down below. Thank you.